Okay, let's go back and look at a rational function here. Let's consider the function f of x equals x squared minus 5x plus 6 all over x minus 3. And as we've discussed in algebra, we know that the denominator cannot equal 0. So I know that x cannot equal 3, or I need to exclude 3 from the domain, however it is you want to think about that. I can also make the claim that f of 3 is undefined. But what I really want to do is I want to describe the behavior of this graph as x is approaching 3. I know at 3 the value is undefined, but maybe I can say some things that as x is getting closer to 3, I can say some things about this function. Well, I notice this function, the numerator factors. It factors out as x minus 3 times x minus 2 all over x minus 3. And if I look at this and I divide out the common factors, I can say, well, f of x is behaving like the function x minus 2 for x not equal to 3. 3 is still excluded from my domain because that's the function that I had up here. However, I can say this function behaves just like the graph of x minus 2, except at x equals 3. So when I go to graph this function, I know it has a y-intercept of -2. And I'm actually going to use a different color here to graph it. I know it has a slope of 1, so I can go up 1 over 1. I'll give myself a little bit of room here on the x-axis. But I can go up 1 over 1, up 1 over 1. If I get to 3 right here, I know that that's where my function is undefined, and so what I have is a hole in my graph, and then I can keep going up 1 over 1 like so, and get a graph of f of x that looks like the linear function x minus 2, except it has a hole in the graph at x equals to 3. So let's take a moment to describe what's actually happening. Describe the behavior of the graph at x equals to 3, because there are some things that I can say. First and foremost, and never lose sight of this, I can say that f of 3 is undefined. If I go back to my original function and I substitute 3 in, I get 0 in the denominator, which I can't do. So f of 3 is clearly undefined. That's why there's a hole there. However, I can say some things that as x approaches 3. So as I'm getting closer to 3, and you could kind of see I was doing that by counting slope, going up 1 over 1, up 1 over 1. Well, as I got to the value x equals 3, my function, if I had kind of kept doing this idea of going up 1 over 1, f of x, the function values, were approaching 1. Notice that it doesn't ever equal 1, but it does approach 1 the same way that x was getting closer to 3. And the above statement which is going to be really important, and we're going to put some notation behind that statement here in a moment, but the above statement doesn't change even if f of 3 were to be defined. And what I mean by that is I could build a piecewise function where I could say, hey, this is my function for every x except 3, but maybe at 3 my function is actually equal to 5, and I could put a point up here at 3, 5, and basically that this statement right here wouldn't change even if there were a point at 3, 5. As I'm getting closer to 3, my function is still getting closer to 1. No matter what I actually did, if I wanted to go in later and define f of 3, this statement right here, this second bullet point, is true. And what we need to do next is we need to take this statement right here and apply some very critical notation so that we can convey this idea moving forward in calculus. Because it's really important to understand that x cannot equal 3 because I would be trying to divide by 0. But I can say that x is getting close to 3. I can say some very specific things about my function. So the next thing we need to do now is we need to put some very important notation behind this second bullet point right here.